Can you hear me? Good, good. So the door is closed, so let's get started. Good afternoon. Thank you for coming to this afternoon session before the party. It's going to be your last session today. My name is Minako. I'm a technical marketing engineer working in data center switching group. That is a business group working on Nexus 9K, ACI, and Hyperfabric. I've been working on ACI almost from the beginning, especially on layer 4, layer 7 service integration. That is the topic for today. I'm sure you have been seeing this slide many times. We have WebEx space. You can post questions even after the session. Since this is kind of large room, I might not be able to take questions on live. But if you have questions, feel free to post any questions related to PBR on this WebEx space. I promise I do try to answer as much as I can. Session objectives. After this session, I hope you will have good understanding of ACI PBR use cases and how it works. That's objective number 1. Objective number 2, to get you understand what's the typical design considerations so that you can think about whether PBR can be applicable to your network or not. And then we're going to talk about ACI PBR for multi-location data center. The assumption is you already know what the ACI is. So this is a level 3 session. So it's supposed to be super technical. So I'm not going to talk about what is ACI, what is bridge domains, VRF, EPG, ESG, and so on. So if you have no idea what ACI is, probably this session is not for you. I'm sorry about that. And here's a note. Because of the limited amount of space in the PowerPoint, I mainly use ESG when we talk about policy and the contract. But from policy and the contract perspective, it doesn't matter whether it's EPG, ESG, or USEG EPG. So you might see myself talking about EPG, ESG interchangeably, but it doesn't matter whether it's EPG or ESG, except multi-site that currently doesn't support ESG yet, but it's going to come. And since I'm lazy enough to write down IPv for IP address only, not IPv6, but PBR perspective, if you have IPv6 endpoint, you can use contract and PBR. So no worries about that. So let's start with, this is the agenda, use case, how forwarding works, FAQs, and then multi-location data center design. Sounds good? So the use case, where can we use PBR? So that might be something we need to think about first. The most important fact to understand is PBR, redirect, is just a contract actions. I assume everybody knows what is contract. Contract is a mandatory component to permit inter-EPG traffic. So basically, if you have two security groups, such as EPG, ESG, external EPG, you must have a contract to allow communication between each other. So that's what contract is. But we have other actions in contract, such as deny, redirect, and copy, which means wherever you have a contract, you can use PBR. Contract is based on source, destination, and filter matching. As long as one of them is different, you can take different action. So let's take a look at a couple of use cases. Typical use case is you have one contract between two different security zones so that they can talk, which means you can enable redirect on that contract so that you can redirect the traffic to firewall. That's the easiest example. But thanks to contract, we have more flexibility. Even if they are in the same subnet, as long as it's in different security group, EPGs or ESGs, you can have a contract, which means you can redirect the traffic. Even between endpoints, in the same security group, we have intra-EPG, intra-ESG contract. You can deny, permit, or redirect. So imagine you need to have such a granular inspection. It's almost impossible in traditional network. So thanks to contract, we have that much flexibility. Since we have contract matching is based on source, destination, and filter, we can think about more use cases. One use case is, let's say you have contract between ESG1 and ESG2. You want to inspect TCP traffic by firewall. Then you can redirect TCP traffic, but you can just let traffic go for the other traffic. So inside of a contract, you can put multiple subjects. And let's say subject 1 is TCP redirect, and then subject 2 is permit IP. So that TCP is redirected, and other traffic is just permitted. You can add more granular deny rule on top of this if you want. Another use case is source-based redirect. So let's say you have some external network, and then you have multiple internal EPGs or ESG. Then you can have, let's say you have contract 1 between ESG1 and L3 out. Action is redirect traffic to firewall 1. Then you can create another contract that has different source destination EPG combination, which means we can take different action. So if you have multiple customers who need different firewalls, you can achieve this by using PBR without touching routing design. So I've been talking about firewall, where we most likely require PBR for incoming and return traffic because firewall usually doesn't change any source destination IP. How about load balancer? Think about the traffic using load balancer. Do we need PBR or not? So incoming traffic, it's most likely we don't need a PBR because traffic is coming to the VIP owned by the load balancer. Anyway, it's coming to LB. But for return traffic, if load balancer does source NAT or load balancer is inside of the routing path, we don't need a PBR. But let's say source NAT is not enabled, load balancer is not in the routing path, then you need a PBR for return traffic only. The key point here is that PBR can be applied to each direction, bidirectional or unidirectional, depending on your security or load balancer requirement. So I hope this kind of enough to get you understand what's the benefit, what's the use case. Then what would be the minimal requirement to use PBR? Two things. One is ACI must be layer 3. If you have completely layers on the ACI fabric, you first need to migrate this to L3 firewall, L3 bridge domain, because we rely to destination MAC and so on. I'm going to talk about it later. But ACI must be layer 3 gateway. The second thing is VRF must be enforced mode. That is the default configuration anyway. The reason is that we need contract. We need contract enforcement to use PBR. If you have been using unenforced mode to permit everything easily in the VRF, you first need to enable this enforcement first. That said, if you want to permit everything, you can use either VZNE or preferred group to permit traffic. I personally recommend VZNE, so let me double click what VZNE is. VZNE is a collection of security groups in a VRF. I would say everybody in the VRF is part of a VZNE. So this is quite useful if you have some provider that everyone needs to talk. Then you can just create one contract with VZNE as a consumer, and then that common provider as a provider. That's it. So that you don't have to create many consumer EPG relationships and so on, which is quite useful. And then, of course, we can enable PBR on that contract. We can even do VZNE to VZNE contract to permit everything in the VRF. More precisely, this VZNE contract allows all of the inter-EPG traffic. Because intra-EPG, within EPG, we don't have contract enforcement. So this allows us to redirect all of the security group to another security group traffic to firewall. That's pretty easy. imagine as a network engineer working with a security team, it's not that easy to negotiate with them around what's the security policy and so on. But you can easily say, oh, we got to redirect everything to firewall, and then we can let firewall team to handle it. That's one of the options we could think of if you want to have some easier way to deal with this. This is also good for switch scale perspective because it's just one access list, one contract rule that is any redirect. So since I briefly touched upon TCAM, so let's double click how it works actually inside of the switch. So let's start with the simplest case. We have one contract with one consumer and one provider. Each EPG, ESG, or external EPG has a unique identifier called class ID or PC tag. In this case, let's say we have 29 for ESG1 and 10934 for ESG2. If we have permit contract between them, we have two zoning rules. So zoning rules is a terminology in ACI. If you type this command, we can check kind of like access list rules inside of the switch. Usually, you don't have to think about it, but for troubleshooting, we might need to take a look at. And then let me bring this up so that we can explain the detail. So here we have two zoning rules. As you can see, 29 to 10934, the action is permit. This is consumer to provider traffic. And of course, we need to allow return traffic. So we have 10934 back to 29. This is also permit. So this is automatically created by directionally. So you don't have to think about what's the ingress or egress access list and so on. It's automatically done thanks to contract. When we enable PBR service graph to that contract, two things will happen. The first thing is Epic allocate class IDs for service device interfaces. If you have two ARM firewall, we're going to have two new class IDs, such as 30 and 32 in this slide. And the second thing is Fabric is going to automatically upgrade the zoning rules to take care of redirect. So let's take a look at step by step. So from consumer to provider, that is from 29 to 10934. The action is redirect, destination group 11. And then after redirect happens, consumer side of firewall receives traffic. Then firewall routes traffic, inspects traffic, and then traffic comes back from firewall, the other side of the firewall, which means the traffic is from 32 to 10934. That one, we don't need a redirect. We just need to permit. And then return traffic from provider to consumer, that is 10934 back to 29. And then the action is redirect, but it's going to different destination because incoming traffic is redirected to consumer side. Return traffic is redirected to the other side. So we are pointing to different destination group. And after that, traffic is coming back from 30 to 29, which is permit. So it's automatically done. But if you see there is something wrong, traffic is dropped, please make sure if you have expected zoning rules and if you have a correct source destination class ID. You might notice that one of the entry has default filter instead of using this original filter 14, such as permit IP or something. So there is a reason, because this is after the first redirection, 32 to 10934. The firewall is supposed to be already inserted. So instead of using a specific filter, we decided to use default any filter so that TCAM in consumption is lower. That said, there is a situation that you need to carry original filter instead of default. So we have an option at service graph template, and then by default, it's allow all. We're going to use default filter, but we can keep original filter. Here is the use case. Let's say you have contract 1, UDP traffic is redirected to firewall 1. That itself is fine. If you have another contract action, such as TCP, we want to redirect the traffic twice. So what's going to happen? So the first action from consumer to provider, 29 to 10934, the action is redirect traffic to firewall 1, which is the same regardless it's UDP or TCP. But after the first redirection, traffic is from 32 to 10934. Here, depending on UDP or TCP, we want to take a different action. Remember I mentioned that contract is based on source, destination, and filter. We need to differentiate based on filter in this case because source and destination is exactly the same. So we need to use original specific filter instead of default. So if you ever have this sort of use case, we have that option. So this is how zoning rule works. So I would like to mention one more important command to check the aliveness information of PBR destination. In the zoning rule, we have destination group 11 and 12 in the previous example. So you can see who is belonging to this destination group. 11.1 is destination group 11, and then 12.1 is destination group 12. And then both are up, and we can use it. And in ACI, the aliveness information of PBR destination is checked by the local service leaf, where destination is directly connected. Then that service leaf distributes the aliveness information to other leaf switches, where we potentially apply policy. So this is how tracking aliveness information distribution works in ACI. We have an important notion called health group. The health group is a group of PBR destinations. So if one of the PBR destinations in the same group is down, we stop using everyone in the same health group. The use case is that, let's say you have two-arm firewall. If one of the interfaces is down for one direction, we should stop using the other side even if this is up. Because when traffic is redirected to the available interface, anyway, we need to route traffic back by using the other side. So we're going to have some black hole. If service device has some intelligence to bring the other interface down by themselves, we probably don't have to care about it. But if you want to have ACI take care of this sort of grouping stuff, please make sure the same firewall having two interfaces, then these two interfaces must be in the same health group. Before going to the next topic, let me double-click zoning rule more because you might have two-node service graph. I've been talking about one-node firewall, but it's most likely you have firewall, load balancer, or firewall IPS, and other combinations. So the rule of thumb is the same, but let me give you one example. So let's say the first node is firewall. PBR is enabled for both directions. And for load balancer, incoming traffic, we don't need the PBR. Traffic is coming to VIP. So PBR is enabled for provider to consumer direction only. Then the zoning rules will be like this. So let's take a look at step by step. So the initial traffic is consumer tries to access to VIP instead of directly accessing to provider. Make sense? So the initial traffic is 29 to 10937, that is VIP. So that one, action is destination group 11, redirect traffic to the consumer side of firewall. Then after firewall routes and inspect traffic, that's going to be coming back from 32, and then destination is still VIP because the firewall doesn't change IP. So 32 to 10937 is permit, and then after load balancer receives traffic, load balancer picks one of the PBR, one of the available provider endpoints, and then translate to destination IP. So traffic is from 5481 and then going to 10937, that is provider. So that is going to be permit. And then the return traffic, 10934 tries to send traffic back to 29 because the assumption here is source NAT was not performed by the load balancer. So 10934 back to 29, the redirect destination is 17. That is the load balancer. Then load balancer changed the source IP address to VIP. So traffic is from VIP going back to consumer, that is 10937 back to 29. And then the redirect destination is 12. And after that, traffic comes back from firewall, which is from 30 to 29, that is permit. So it's pretty straightforward, and it's probably something you have been dealing with this without ACI. But the point here is that it's automatically updated based on what we define in contract and service graph. One important traffic to make this work is keep alive. It's most likely load balancer sends some keep alive traffic from load balancer itself to backend servers. Would that work in this zoning rule? Actually, it doesn't work because this is bidirectional keep alive. The server needs to respond it back to the load balancer. So we have a permit rule for 5481 to 10934, but we don't have a permit rule for the return traffic by default. So if you want to get service device talk to consumer provider directory, we need to enable this direct connect option at the service graph template. So we talked about zoning rules, what's the expected policy action, but the most important part is how forwarding works, what's the destination IP, MAC lookup, and so on. So let's take a look at step by step. So we have 192.168.1.1 on the left and 2.1 on the right. And let's say 1.1 is consumer, and then 2.1 is provider. You already have a contract, and then firewall is 2R. For just illustration purpose, I put everyone under the defined leaf, but you can put anyone on anywhere. So let's say consumer sends traffic to the provider, 1.1 to 2.1. The ACI is a gateway, so the destination MAC is bridge domain leaf MAC. Traffic is going to leaf 1, and then let's say leaf 1 doesn't know where 2.1 is located yet. Then traffic is going to spine, and then spine has an endpoint database saying that 2.1 is under leaf 3. So traffic is going to leaf 3, and here, source class information is inside of VXLAN header, and destination is local from leaf 3 perspective. So leaf 3 can identify who is source class and then what's the destination class. From consumer to provider, the action is redirect, as we just checked in the zoning rule. So when policy, PBR policy is applied by leaf, what happens is that we relay to destination MAC. This comes from configuration. So we define PBR destination by specifying IP and MAC and the BD. So as you can see here, destination MAC and destination segment ID is rewritten by keeping source and destination IP exactly same. So it's going to spine proxy, and then traffic is going to the consumer side of a firewall in this example. Here, one important note, if you really want to know how forwarding works, even if the PBR destination is under the same leaf, such as leaf 3, traffic is once bounced to spine. It's going to spine proxy once, because we rewrite destination MAC and the destination segment ID. So after firewall permits traffic, routes traffic, traffic comes back to leaf 2. If you don't see traffic coming back, it's most likely firewall drops packet. So here, the destination IP is the same, 2.1. So it's just routed, but redirection doesn't happen again because destination class is still provider, but source class is not consumer. It's consumer side of firewall. The action for this combination is permit, so we just permit traffic. And here, another important magic happens behind the scene is leaf 3 doesn't run 192.168.1.1 from leaf 2, because as you can see in the bottom of this screen, 1.1 is actually under leaf 1. So we shouldn't run this from service leaf. So it's automatically disabled. Data plane IP running is automatically disabled on the service EPG where PBR is configured. So you don't have to pay attention to this, but I just want to let you know that how magic is happening. The return traffic is same, 2.1 talk to 1.1. And here, let's say leaf 3 already knows the destination endpoint 1.1. So here, leaf 3 can apply policy on the ingress. Here, we rewrite the destination MAC to the provider side of firewall. Traffic is going to the provider side of the firewall. Then firewall routes traffic, inspects traffic. Then traffic is going back to consumer finally. Here, redirect doesn't happen again because this is from firewall consumer to consumer. That is permit action. And then 2.1 is not learned from this packet because this is after PBR. Data plane IP learning is disabled on the service EPG where PBR is enabled. Then traffic can go back to consumer finally. So this is how end-to-end policy enforcement works. So you might notice that ingress or egress enforcement would be different. Where policy is applied could be different depending on endpoint learning status. So it's actually depending on the contract configuration. So I'm not going to talk about too much detail here. This is just for your reference if you are wondering where policy is supposed to be applied. So you can take a look at the ACI contract guide for detail. That said, let me explain how ingress and egress leaf enforcement work. So let's say we have a contract between ESG1 and ESG2. If you have intra-VRF, ESG to ESG, or EPG to EPG contract, this could be ingress or egress enforcement. It depends on endpoint learning status. Let's say if ingress leaf, leaf 1, knows where 2.1 is located, then source and destination class IDs can be resolved. So leaf 1 can apply policy. And leaf 1 put 1 bit, policy applied bit set to 1 in VXLAN header. So that when leaf 2, egress leaf receives traffic, leaf 2 open up packet, taking a look at the policy applied bit. If it's set to 1, leaf 2 doesn't apply policy because policy was applied by leaf 1. So that's ingress enforcement. If policy was not applied because destination class ID cannot be resolved in the egress leaf, then policy applied bit is set to 0, so that leaf 2 needs to apply policy so that we can ensure either ingress or ingress leaf apply policy. So this is how policy enforcement works. So when you do troubleshooting, depending on endpoint learning status, policy enforcement location could be different. So please make sure if you want to double check policy is applied or not, check ingress and egress leaf. So we talked about a lot of detail. So the next step is how would it work if you have a combination of permit, deny, and redirect? Because it's most likely you have a combination of permit and redirect. So the rule of thumb is more specific rule will win. It should make sense. So if you have a specific EPG to EPG contract, that wins over specific to VZNE or VZNE to specific. That wins over VZNE to VZNE. So more specific rules should win. If you have same zoning rule priority, deny is the strongest. This is a strong statement. So deny should win. If you have a specific filter, let's say permit HTTP and permit TCP, HTTP is more specific. So specific rule will always win. So you can take a look at the contract guide for detail, but probably you are wondering what these actually mean. So let me give you 3 examples. The first example is, let's say you have newly deployed VRF. Initially, you have no idea what sort of security policy you need to enforce. So you can start with VZNE to VZNE permit contract so that everything is permitted. It's easy. And then it's going to be just one zoning rule. So 0 represents any. So any to any specific filter, in this example 74, but it could be different depending on timing. And then the action is permit. This is one zoning rule that can permit everything. So thanks to this, ESG1 talks to ESG2, this is permit. ESG1 talks to external EPG, this is also permit. And then ESG2 talks to external EPG, this is also permit. Easy. And then a couple of days later, you have a requirement to inspect the TCP traffic. Between 2 security groups, you want to enforce policy by firewall. Then you can create another subject under the existing contract saying redirect to TCP. Then it's going to create another zoning rule. Any to any, 14 is TCP. 14 is TCP, 74 is permit IP, for example. And then you can have permit and redirect action, but zoning rule priority on the right, it's same, 17. So which would win? The rule of thumb is specific protocol win. So if you have TCP traffic between ESG1 and ESG2, what would be the action? Redirect. Because redirect rule has more specific filter, and this traffic is TCP. This should be redirected. But if you have a UDP traffic, this will be permit, because we still have VZNE permit IP rule. So this is what I meant specific protocol win. And then the third example is, let's say you start with VZNE permit IP that allow everything, but you want north-south perimeter firewall. Then you can create VZNE to external EPG contract, redirect IP traffic. And then you need east-west inspection. But it's only for TCP traffic, for specific combination. Then what would happen? Here's the quiz. So we have TCP traffic between ESG1 and ESG2. What would be the action? Redirect, because we have the most specific rule here is ESG1 to ESG2, redirect to TCP. How about IP traffic between ESG1 and the external EPG? This will be also redirect, but this is going to be redirected to north-south firewall instead of east-west. If you have UDP traffic between ESG1 and ESG2, this is permit, yes. Thank you, someone can answer that for me. So rule of thumb-wise, it's pretty simple. More specific rule will win. But if you can start combining a lot of combinations, it's easy to get confused. So please get back and then think about what's the exact combination and what's the expected traffic behavior. So this is just for your reference. It's going to be like this. I'm not going to explain too much detail, but as you can see here, specific to specific rule wins over specific to VZNE, that wins over any to any. So there are so many zoning rules and so on. So let's step back and then talk about what's the typical design considerations. So I'm going to walk through a couple of commonly asked questions and then explain why this matters. So the most commonly asked question is 1 arm or 2 arm, which is better? The answer is it depends. I'm not quite answer the question, but I'm going to explain what's the pros and the cons. So 1 arm is really nice in terms of routing design. So it's easy to get confused between firewall team and the network team, what's the expected routing configuration. So you can just have one static route on the firewall, that's it. Firewall team would be happy because it's pretty simple. And it's actually the requirement if you have intra-subnet redirection, because imagine source and destination are in the same subnet, then anyway we need to use one interface. That said, your firewall team might not like it, because if they have been using security level based on interface, combining things in one interface, they're going to need to redesign security level setting. And actually, by default, some of the firewall vendors, including Cisco ASA FTD, doesn't allow intra-interface traffic by default, although we have an option to make this work. So if you really need 2 arms, that's completely fine, but you need to deal with routing. So if firewall routing doesn't make sense, traffic doesn't work, although we can redirect anything to firewall. So it depends. The next question is, can we reuse the same PBR destination multiple times? The answer is yes. I've been talking about just one consumer, one provider, but practically speaking, you have tons of EPGs potentially. So if you have multiple consumers and multiple providers, you can just use the same firewall. Or even you have multiple contracts, different consumer-provider EPG combination. If you want to use the same PBR functionality for the same firewall, you can just reuse the same service graph, same PBR destination. That's completely fine. So the easiest option is having 1 arm firewall and then redirect everything to there. But let's say if you have multiple security levels, different interface, you need to deal with this. But the point here is that you don't have to have a lot of different firewalls only for PBR. You can reuse it. That said, a couple of considerations. If you have hundreds of contracts and then a lot of consumers and a lot of providers, the combination could be huge. So it's not good for TCAM consumption, although configuration looks easy. So if you have too many combinations, I would recommend the use of Brkdcn or ESG to simplify your rule, because at the end of the day, you are the one who need to manage this security rule. The second point is, although we can redirect anything, if firewall cannot handle it, routing-wise, firewall scale-wise, it doesn't work. So please think about if it makes sense from firewall perspective. The next question is, what sort of devices can be PBR destinations? As we discussed, we just redirect traffic. We just change destination MAC address. We are vendor neutral. You can use any firewall or router or any load balancer as a PBR destinations. To be honest, ACI doesn't care whether it's Cisco firewall or other firewall. That said, prior to 5.0, we must use layer 3 device. Starting from 5.0, we can start supporting layer 1, layer 2 PBR so that you can redirect traffic even though this is inline IPS or layer 2 transparent firewall. And we can actually put different types of devices in the same contract. We typically call it the service chain. So let's say you redirect the traffic to inline IPS first, and then transparent firewall, and then finally layer 3 PBR for load balancer. So you can concatenate different types of service devices. It's pretty flexible. And then the last question is, what are the high availability options. I'm going to talk about 3 options. The most commonly and traditionally used is active standby HA pair or active-active cluster. You have 2 devices, active and standby, and the active device takes care of the shared IP. And then if active device is down for some reason, then standby device elevates itself to be inactive, and by sending a gap or some other traffic to take ownership of that shared IP, such as 10111. So in this case, PBR is not mandatory because 10111 could be just a destination next hop. If it's PBR, it's one PBR destination IP, that is 10111, for example, and from configuration-wise, it's one logical device with 2 actual concrete devices. So this should be pretty straightforward. The second case is active-active cluster. Unlike active standby, everyone in the same group, same cluster, act as an active. And then they are sharing the same IP. Here, since this is a Cisco Live session, I'm going to talk about Cisco ASA FTD clustering behavior. To be honest, each firewall vendor has slightly different implementation of active-active cluster. So if you have non-Cisco active-active cluster question, please come talk to me offline. I'm going to talk about the Cisco firewall active-active cluster in this session. So in this case, this is one destination IP. This is a shared IP across multiple devices in the same cluster. And then the important requirement is they are acting as if it's one single device. I'm going to double-click this next. And then the third example is independent active nodes. So let's say you have 6 devices, 3 active standby pairs, 3 independent IPs. In that case, we need to load balance traffic. So ACI PBR has a capability called symmetric PBR to load balance traffic to making sure incoming and return traffic goes to the same PBR destination. So I'm going to double-click second and third example because first example is pretty straightforward. In case of symmetric PBR, independent active nodes, it's going to be multiple destination IPs, one logical device with multiple concrete devices. So let's double-click active-active cluster. I mentioned that they are supposed to act as if it's one device. The reason is that since they are using the same IP, if they are connected and a different location in fabric, it's not good because it's basically IP address flapping. Regardless ACI or not, that's bad, right? So they must be connected as if it's one single device, meaning they must be connected through one big port channel. Except multi-port case. In case of multi-port, you have 2 locations or even more than 2 locations. Then you want to put firewalls in each site, each pod. Then you can distribute active-active firewalls in the same cluster across different locations as long as the location is unique in each pod. So in that case, service leaf in port 1 says 10111 is here. And then another service leaf in port 2 says, oh, 10111 is here. So if it's just a general behavior, it doesn't work because it's going to confuse fabric because basically it's IP address flapping. But ACI multi-port has a functionality called Anycast service. So when we enable Anycast service on this particular IP, the spines in each pod, they prefer local location because it makes sense, it's close. And then they exchange 10111 location across pods by using EVPN so that as long as local location is up, that location is preferred. But let's say all of the firewall in the same pod is down, they start using the remote location so that we can minimize traffic hairpinning, and also we can keep traffic very high availability. So I'm going to double click as part of multi-location data center section. So independent active nodes. So imagine you start with one firewall and then start seeing traffic is increasing. Traditionally, you might need to replace firewall with a bigger appliance or buying big appliance beforehand. But instead, in ACI symmetric PBR, you can just add the PBR destination IPs in the same group so that ACI is going to load balance traffic. Based on hash, we keep same flow going to the same firewall. So it's good for scale. And compared to active-active clustering, you can put these firewalls anywhere in the fabric. Because of the illustration, I put everything in the same leaf, same service leaf node, but it can be under different leaf nodes. So from high availability perspective, this might be better than active-active clustering. Since we briefly touched upon symmetric PBR and hash, so let me double-click hashing behavior. So by default, it's source IP, destination IP, and the protocol number. So even if it's coming from same IP, depending on destination IP, it could go to different PBR destination. So instead, you might want to keep same user, same IP going through the same device. Then you can use source IP only and the destination IP only hashing. But when you configure it, please be careful. You can make sure incoming and return traffic will go to the same device. So let's say if you use source IP-based hash for incoming traffic, you need to make sure you're going to use destination IP-based hash for return traffic, because we need to get the same result to keep traffic symmetric. Source IP of incoming traffic is destination IP for the return traffic, right? So if you put same IP for the hash calculation, you can get the same result. As a result, you can keep incoming and return traffic go to the same PBR destination. If you have multiple PBR destinations, what if one of the devices is down? So by default, it's going to be rehashed. So it's similar to routing ECMP port channel. It's going to be rehashed. If it's port channel or just general routing, you don't really care. But if it's stateful L4, L7 device, there might be a concern because let's say the light blue user 1 was going through the destination number 1, and then destination number 1 is down. So light blue is going through different node. That's fine, it's expected. But let's say green that was going through the third node is now going through fourth node. The fourth node doesn't know the existing connection for green, then existing connection might be impacted. If you don't like it, we can enable resilient hash feature, meaning if one of the devices is down, the traffic that was going through the failed device will be redirected to one of the available nodes. But other flows, such as green and purple in this slide, they are going through the same node. So existing sessions that were going through available nodes are fine. Obviously, user 1 got impacted, although. That said, the important part is the blue user, light blue user, is rerouted to the second node, one of the available nodes. So it's not going to be redistributed again across 3 available nodes. So in this example, the second device, that device needs to handle almost double the amount of traffic. So thinking about the capacity planning. So in steady state, thinking about failure, you probably need to set a limit. Let's say, oh, in steady state, we should set, let's say, 50%, because if one of the devices failed, that remaining device needs to handle double the amount of traffic. So if you don't like it, you can enable backup feature. So the backup device doesn't receive traffic unless something wrong. If a device is down, the traffic that was going through the failed device is now redirected to backup node. Whether resilient hash, disable, enable backup, what would be the best option? So it depends, I would say. If you have short-lived connection, probably you don't care about resiliency. You can just let the user reinitiate the connection. Then resilient hashing disabled would be better distribution. And if you have, let's say, 2 or 3 nodes, backup might not make sense. We do need a math, but usually more than 4 or 5 devices, backup device would make sense. So it depends. So these are the typically commonly asked design questions. So if you have any more, please come to me, and we can discuss about the design thing. So the last topic today, the last 40 minutes of this presentation, I'm going to talk about multi-location data centers. So let me start with what's the general challenge related to multi-location data center with stateful device. It's fine you don't have a multi-site, multi-port. It's a general consideration. So let's say you have 2 locations, site 1, site 2. You have a subnet stretched, 10.1.1 and 10.1.1.2 distributed across locations. And then you put a firewall, independent firewall in site 1 and site 2 separately. If traffic is coming to site 1, but destination is in site 2, this could happen because subnet is stretched. Then the return traffic is most likely going through the local exit. That device doesn't know incoming traffic, then it's most likely firewall will drop traffic. The key point here is that keeping traffic symmetric is very important, especially if you stretch subnets. So I'm going to talk about how we deal with this for multi-port and multi-site. So multi-port, we have 3 options. The first option is active standby across ports. In this case, we don't need to deal with the asymmetric traffic because traffic is anyway go to active device. But let's say if you have endpoints in port 2 on the right, then traffic needs to go through port 1 and then coming back. If the location is close enough, you probably don't care. But if you do care, active cluster might be better. Then I'm going to double click on this option, how to eliminate traffic hairpinning. And then the last option is active standby in each pod. We can use symmetric PBR, but usually the first and the second option are common in multi-pod. So let me double click the second option because the first option should be straightforward. So active cluster across pods. Let's say we have port 1, port 2, web EPG is stretched. And then we have active cluster across pods. IP is 10.1.1.1, and then enable any cast service that allows us to prefer local location. Then, let's say you have north-south traffic, external EPG to web EPG traffic, and then PBR is enabled. For north-south contract, external EPG and specific EPG contract, policy is always applied on compute leaf instead of border leaf. And the compute leaf applies policy, and then rewrite the destination MAC to PBR destination, that is 10.1.1.1's MAC. That one going to port 1 spine, and then port 1 spine prefer the local location. So we can select local destination that is more efficient instead of using firewall in defined pod. Even if traffic is coming into port 2, compute leaf apply policy. And here, port 2 spine prefers the local location in port 2. So we can use localized traffic, no traffic hairpinning, and the return traffic going to be enforced by the same compute leaf. So we can keep traffic symmetric, and we can eliminate traffic hairpinning. So that is how active cluster works with ACI multi-pod. For east or west, if it's intra-pod traffic, regardless it's ingress or egress traffic, traffic will be redirected to the firewall in the local pod. So there's no traffic happening. We are happy with that. One consideration is, let's say you have inter-pod traffic, web to app, east or west. Then the policy enforcement depends on endpoint landing status. So let's say ingress leaf knows the destination already, then ingress leaf applies policy, firewall in port 1 is inserted, and then traffic is going to the destination. If return traffic is also ingress enforcement, because of some reason, ingress leaf in port 2 lands the destination, then redirect could happen inside of port 2, then traffic is going to firewall in port 2. In that case, thanks to active-active cluster, Cisco ASAFTD is smart enough to identify who is the owner of this session. So they have additional control link. This is another VLAN. This is just a logical link to carry traffic back to the original owner in port 1. So even if asymmetric traffic could happen for inter-port traffic, we can make this end-to-end stateful inspection work. So this is how active-active cluster multi-port work. So multi-site, we have 3 options, but compared to multi-port, we recommend the last option, independent firewall in each site. It's because the intention of multi-site is fault domain isolation. As you can see here, each site has different APIC cluster. Why don't we have independent firewall cluster or HA pair in each site? So we're going to double click on this multi-site independent firewall in each site. For north-south, external EPG to web EPG, it's pretty much similar to multi-port. We apply policy on the compute leaf, and then in each site, they use local site firewall. So there's no traffic happening. Even if traffic comes into site 1, going to site 2, policy is applied by compute leaf, and then firewall in the compute leaf site is inserted for both directions. So this is how north-south redirection work. And for east or west, we have slightly different behavior because it could be ingress or egress enforcement. So for web to app, inter-site east or west traffic, we always apply policy on the provider leaf. That would make sense because provider is the one providing service. So having them take care of security policy would make sense. So provider leaf applies policy so that we can keep traffic symmetric, but you might be wondering, return traffic, what if provider leaf doesn't know the consumer endpoint? So to make sure provider leaf always able to resolve destination class ID, we must configure consumer EPG subnet. This is the requirement for multi-site east or west PBR. We must configure consumer EPG subnet, which means the design-wise, it's not really application-centric. It's one BD subnet, one EPG, network-centric. If you don't like it, I have some additional slides to explain how we tackle this challenge. Before that, let me briefly explain how we ensure the provider leaf enforcement. Because ingress leaf could potentially resolve destination class ID, but we bypass enforcement because of special rule. I'm going to use this example. So let's say we have 32271 to 32272. We have 2 redirection rule, but for consumer to provider, 71 to 72, we have redirect override option inside of action. So what it does is that if destination is not a local endpoint, we don't apply policy. So consumer leaf just permit traffic without applying policy. Policy applied bit is set to 0. Then provider leaf apply policy. This is how we ensure the provider leaf enforcement happens. If the ingress leaf knows the destination locally, ingress leaf can apply policy. So this is how east-west EPG to EPG contract with PBR works in multi-site. And we have been supporting this since 4.0, several years ago. Then one of the common asks is, can we do with any PBR in multi-site? So it's been a common ask, and then starting from 6.0, almost more than a year ago, we started supporting with any to EPG, with any to with any. And we introduced new configuration workflow that is much, much simpler than Epic configuration. So the last 30 minutes of this session, I'm going to explain how it works, including demo. So with any to EPG. So this is quite simple and useful if you have some common policy. If everyone needs to talk to some application, but you need to inspect traffic by firewall, then it would be nice to support with any to EPG PBR in multi-site. So the challenge is obviously how to keep traffic symmetric because we have multi-location data center. So that one, we use provider leaf enforcement similar to what we just discussed for EPG to EPG. So that's fine, but for consumer EPG subnet configuration, we don't like it because imagine you have a lot of EPGs with application-centric fashion. It's very hard to figure it out what's the subnet for each consumer. So we need to resolve this consideration, and then we introduce new behavior that is called conversational learning. So I'm going to double-click how it works. So with any to EPG PBR in multi-site, let's say we have site 1, site 2. We have independent firewall in each site, web in site 1, app in site 2. Then we apply policy on the provider leaf. Consumer to provider direction, this should be fine. Provider leaf applies policy, that's it. Return traffic, if provider leaf knows the consumer destination, provider leaf just applies the policy, and then firewall 2 is inserted. That's it, right? What if ingress leaf doesn't know the destination? Then we have no choice but to permit traffic. Policy applied bit is set to 0. So the destination leaf in site 1 receives traffic, but we want firewall 2 in site 2 is inserted. So we have new behavior. If destination leaf receives traffic that was supposed to be inspected by source leaf, but PA equal policy applied bit is 0. So this is from site 2, but firewall in site 2 must be inserted. So the destination leaf redirects traffic back to firewall in site 2, the source site. So this is a new behavior to ensure firewall is always inserted in provider site. And then after that inspection, traffic is just permitted, and then arriving back to site 1, which is good, but we have unnecessary traffic hairpinning. But this wouldn't happen continuously because we introduce conversational learning. So when ingress leaf in provider site implicitly permit traffic, destination leaf sends traffic back. At the same time, this destination leaf sends some special packet that gets ingress leaf in site 2 learn the destination. So since original packet is from 2.1 to 1.1, so the destination leaf in site 1 flip this. The source IP of this special packet is 1.1, then destination is 2.1. Then this purple line, this traffic receives on the leaf in site 2, this is from 1.1. So that packet gets ingress leaf, learn the destination. So after conversational learning is done, we can ensure provider leaf always apply policy. So this is how BZNE, EPG, PBR works in multi-site without specifying any consumer EPG subnet. So this is BZNE to EPG. How about BZNE to BZNE? So the challenge is how to keep traffic symmetric, because since consumer and provider is the same, there is no notion of provider side or consumer side. So we cannot stick on provider leaf enforcement. And we can also need to make sure how to resolve destination class ID. That one we, again, use conversational learning. But how to keep traffic symmetric? So we introduce new behavior for BZNE to BZNE in multi-site. So if you have inter-site traffic, we need to pay attention about traffic hairpinning and also traffic symmetricity. What if we insert firewall in both source and destination site? Then we don't have to care about traffic asymmetricity because both of the firewalls are inserted for both directions. For intra-site traffic, we don't redirect traffic twice. So this is a summary, but it's probably hard to understand what actually means. So let me illustrate this. So let's say if we have BZNE contract with PBR in multi-site, web in site 1, app in site 2. PBR is enabled. So ingress leaf in site 1, we redirect traffic to firewall 1. So source site has firewall inspection. And then after firewall 1 receives traffic, traffic is going to the destination. In the previous example, that's it, right? But we have new behavior. If it's BZNE, and if traffic was redirected in the source site, the destination site redirects traffic again to ensure both firewall in source and destination are inserted. And then after firewall 2 inspects traffic, this is intra-site traffic between firewall 2 and the app endpoint inside 2. No additional redirect happen. So you might be wondering how we can ensure the destination leaf can identify firewall was inserted in source site. So we talked about policy applied bit almost an hour ago. So let me explain how we can identify policy was applied and redirect was happening. So policy applied bit, we talked about that 1.1 talk to 2.1. If policy is applied in the ingress leaf, policy applied bit in the VXN header is set to 1 so that leaf 2 can identify if policy was applied or not. So this is the indication of what was happening in the ingress. We actually have 2 bits for policy applied bit. So we have been using, if both are set to 1, policy applied bit is 1, which means ingress leaf was applying policy. So egress leaf doesn't have to apply policy. And if it's set to 0, egress leaf needs to apply policy. So we can indicate one more situation because we have 2 bits. So we introduced SP equals 0, DP equals 1 is used for traffic from service EPG to indicate traffic was redirected in source site, and then that needs to be redirected again in the destination site. So let me go back and then take a look at how forwarding works for BZNE web to app inter-site traffic. So ingress leaf applies policy, traffic is redirected to local firewall, and then from service EPG to destination, we set this special flag. So this is the indication firewall was inserted. Then when traffic is coming in to destination site, if traffic is from another site, and if SP equals 0, DP equals 1, that means another site had a firewall inspection. And then since this is VZNE to VZNE, the destination leaf needs to apply policy again so that firewall 2 is inserted. After that, from firewall 2 to destination, we have that special flag again, but redirection doesn't happen again because it's intra-site traffic. The condition is if SP equals 0, DP equals 1 are set, and if traffic is coming from another site, this can be identified by checking source step information, because each site has a unique source step. And then the return traffic is the same. Ingress leaf apply policy, firewall 2 is inserted, and then traffic from firewall 2 has this special flag, and then the destination leaf in site 1 receives traffic from site 2, and then it was redirected in site 2. So destination leaf in site 1 needs to redirect traffic again, so firewall 1 is also inserted. And then redirection doesn't happen for intra-site traffic. So this is how VZNE PBR work, ensuring both source and destination site have a firewall inspection. Again, if it's intra-site, it doesn't happen twice. It happens only when you have inter-site traffic. So even if you have multi-site, you don't have to pay attention on this for all of the traffic, because it's most likely you would prefer to select intra-site traffic instead of having some workload talking to the workload in different site. Then, if ingress leaf doesn't know the destination, there's no choice but to permit traffic, but we have conversational learning and also the ability to send traffic back to the source site, similar to the previous example. So even if it's VZNE to VZNE, there's no endpoint is learned. The destination leaf sends traffic back to the source site firewall. And then after that, firewall sends traffic to destination. Here we have new special behavior, SP0, DP equals 1. Then traffic is redirected again in the destination site, and then destination site firewall is inserted. So that's it. And then at the same time, we have a conversational learning packet. Ingress leaf doesn't know the destination, so egress, destination leaf inside 2 sends traffic back to the original ingress leaf, so that ingress leaf can learn where 2.1 is located. So after conversational learning is done, it's always ingress enforcement. So this is how VZNE PBR work in multi-site. So that's going to be a baseline. But you might notice that, oh, probably for this specific combination or intra-EPG traffic, we don't need a firewall. We want to bypass firewall. So that's pretty easy. So let me explain intra-EPG and inter-EPG firewall bypass. So intra-EPG, you might remember that it's always permit. So you don't have to add anything. So you can use VZNE PBR that is applicable only for inter-EPG traffic. So intra-EPG, without touching anything, it's going to be just permit, no firewall. So let's say ingress leaf in site 1 receives traffic. Regardless its destination is known or not, it's just permit. If ingress leaf apply policy applied bit is set to 1, and then the destination doesn't apply policy again. If ingress leaf doesn't apply policy, egress leaf applies policy. We don't hit any special VZNE rule because, as I mentioned, specific rule will win. Any to any is the lowest priority. You can easily bypass that traffic. for specific EPG to EPG or EPG with any traffic to bypass firewall, this is also easy. We talked about gory detail of PBR. You might be tired, but permit contract is super easy. It's just a contract. So if you have a specific web to app permit contract, that's specific to specific. That wins over any to any, right? We talked about the contract priority. So you can just add permit contract to bypass firewall. So it's pretty easy. So if you have a web endpoint talk to app endpoint, let's say if ingress leaf knows destination endpoint, PA equal 1, egress leaf doesn't apply policy. If ingress leaf doesn't know the destination, it's implicitly permit, but egress leaf can apply policy. Because specific to specific rule wins over any to any. So with any to EPG, PBR, I talked about so many details, but you usually don't have to think about it unless you need to troubleshoot something. And also from design-wise, it's pretty easy. You can start with any redirection for firewall, and if you don't need it, you can just bypass it by adding a specific contract. It sounds difficult, but imagine you need to deal with how to keep traffic symmetric by yourself without contract. As I mentioned, it's a general consideration. If you have a multi-location data center with IP address stretched, you need to deal with how to keep traffic symmetric for stateful inspection. So this is a summary. So we talked about EPG to EPG, EPG to L3 out, and then the new feature is VZNE to VZNE, VZNE to EPG, and also VZNE to L3 out and L3 out to L3 out. Except VZNE to EPG, we need redirection in both sites. For inter-site traffic, we need to support one node, one ARM, intra-VRF only. Starting from 6.13, that's the latest FCS code, we can do VZNE to EPG, two node, two ARM. But other use case, you need one node, one ARM. So by using this new feature, you don't need to configure EPG subnets anymore. So you can do more application-centric fashion. By configuring specific EPG to EPG, you can bypass firewall. You still need firewall in each site. If you have site 1, site 2, you must have independent firewall in each site. ESG with PBR is not yet supported in multi-site, but it's coming in 6.14. So if I can have similar session next time, I can talk about ESG multi-site contract enforcement. So this is the really last part of my presentation. So I'm going to talk about configuration workflow. So we talked about how it works. These are the design considerations. But the last step is you got to configure it. And then to be honest, APIC configuration, we are evolving this service graph PBR feature slightly. So we kept adding some objects. And then to be honest, it's not that easy. But let me recap how we configure service graph on APIC, and then how it would look like in Nexus dashboard. So on APIC, obviously we need a contract, because redirect is contract action. I kept saying it. And then we have a service graph template to define what's the service function and what's the order of service function. So that we need to configure it. And then service graph template is attached to contract. So that's a general step, but we need to prepare a lot of things to let APIC know what we need to program. The first object is L4, L7 device. Because we need to create a service EPG, we need to deploy VLANs for service device. So similar to EPG static path binding or VMM domain, we need to define physical domain or VMM domain. If it's physical domain where this service device is connected, we need to configure that. And then you might have multiple contracts, and then depending on contract, let's say contract 1, you want to use firewall 1. If it's contract 2, you want to use another firewall. So we need to define device selection policy based on contract, service graph template, and if you have multiple nodes in the service graph, you need to define this. And also, as part of that device selection policy, we need to define where to place this service device interface, which means bridge domain. So there are a lot of objects you need to deal with, but I haven't talked about the PBR configuration yet. So we have PBR configuration in addition to this. So we need to define PBR policy that has PBR destination IPs and MAC optionally. And then if you want to tweak hash option, resilient hash, tracking configuration, you need to define that. And then IPSLA tracking policy allows us to configure interval and then protocol. And also we need to define health group. So the last two slides, probably you saw that we might need to deal with 10 or 20 objects. But this is kind of like a building block that we need to define, regardless it's ACI or not, but it sounds tedious. So in multi-site, initially, we have two locations of configuration. So on APIC, in each site, we have APIC cluster. So in each site, we need to define policy, where device is connected, what's the PBR destination IP, and the tracking policy. And then on NDO, we define contract, service graph template, and then concatenating things together. So we have two locations to configure. So it's not quite intuitive, so we redesign the configuration workflow. So it's just 3 steps. And the first step is optional. If you need tracking, IPSLA policy for both sites. The second one is service device template. And the third step is associate that service device to contract. So the last part of this presentation, I'm going to show the demo that I recorded, how to configure service graph with any from scratch in multi-site. So let me play this. So I have service chaining application template, and I already defined a couple of EPGs and VRF. We have 2 sites. So we have a couple of EPGs, 1 VRF, a couple of bridge domains. And then I have web endpoint in site 1, 10.1.11, and then app endpoint in site 2, 10.1.2.22. So I send ping from web to app. Does that work? No, right? I have the configure contract. So let me create with any to with any permit contract without PBR. It's pretty straightforward. You can just create one contract called with any to with any, and then going to VRF. And then here in VRF, we associate this contract. This with any is a consumer and also the provider. So this is just creating with any to with any contract in the VRF. That basically allows everything. So let me push this new with any contract configuration to site 1 to site 2. Boom. So it's immediately allowing traffic between web and app. Then the next step is create PBR. So let me first create IPSLA policy that is in tenant policy. This is optional, but I highly recommend enabling tracking. So let me create IPSLA monitoring policy. So let's say ICMP 3 second. And then once I create this, I'm going to push this to both sites, site 1 and site 2, and then push it. But so far, nothing is happening for the traffic because I just create IPSLA policy. I haven't enabled the PBR yet. So the next step is create a service device. This is where we define this is going to be L3 firewall, L2 firewall, and so on. So since this is with any, I'm going to create one num L3 firewall. So let's say layer 3 firewall. This is L3 one num, and since this is one num, I need to define one bridge domain for this arm. And then redirect is enable, and the IPSLA monitoring policy, I just select the one that I just created. We have advanced setting. such as hashing and so on, but I don't use it. I'm going to just disable it. And then the next step is we need to define where this service device is connected. This is per site configuration. So for each site, I'm going to use virtual firewall, so selecting VMM domain in site 1. And then we don't have to specify VLAN, it's automatically done. I have 2 firewalls in each site, active and standby firewall. So I got to select a standby firewall and active firewall, and then selecting which interface we're going to use. So I'm selecting the second firewall in site 1, and then selecting the same interface. Since this is active standby, I just have one PBR destination IP. So that's it. So I'm going to repeat doing this for site 2. You can use different physical or virtual domain, but I'm going to just use VMM domain for both sites. And again, selecting the same service bridge domain, and then selecting another firewall pair, site 2 firewall 1, and site 2 firewall 2. Of course, if you have multiple firewalls, you can use independent HA pairs inside of each site. Since each site has independent firewall, this is going to be the second PBR destination IP. So that's it. So let me push this. So far, from forwarding-wise, nothing happens because I just create device and the policy. It's not associated to contract. PBR is not yet enabled to the contract. So we have device policy. So we are fully ready to enable PBR for the contract in with any to with any. Before associating this device to the contract, we need to click 2 things. Because we introduce new conversational learning behavior, in the VRF, we need to enable L3 multicast and site-aware policy enforcement. This is for kind of like a magic, so for new behavior. And then going to contract, here we can see who is the source and who is the provider. So we just need to select what service device you want to insert between them. So redirect is enabled on both directions. So that's pretty much it. So once you have service device defined, then you can just enable this service device, associate this service device to whatever contract you want. So by pushing this, it's going to take probably a couple of minutes, depending on how many contracts filter you have. But here, in each site, the service device deployed graph instance are there. So service graph is deployed. And what happens is that zoning rules are updated, as we discussed in the beginning of the session. And if it's virtual device, we create service EPG port group, and then it's automatically attached. Because we define which device and the port should be used for this PBR deployment. After keep alive is successfully done, firewall in each site should receive traffic because we are sending traffic between web and app across sites. So this is a firewall in site 1. So now we see some ICMP traffic. This is between web and app, and this is site 2 firewall. This also sees traffic because for with any multi-site PBR, we redirect traffic in both of the sites. And here, ping is obviously working. And then if you don't need firewall anymore, you can just simply remove it. And then graph is removed, and then traffic is just permitted. So on each site, we don't have device anymore. And then from VM perspective, we have policy, a port group associated, but it's already removed. So that's very quick overview of how simple it is. I think compared to Epic, I think it's pretty simple. With that, that brought us to the end of the session. So here's the summary. We talked about how PBR works, what's the benefit, design tips, and it's pretty flexible. We can do flexible redirection based on contract. We can do intra-EPG, intra-ESG. We can do any-to-any, and we can scale easily by using symmetric PBR. We can use L1, L2, L3. We take care of multi-location data center design. We have with any PBR. NDO configuration gets much simpler. And then finally, ESG PBR will be available in 6.1.4. So if you need more detail, please post question on the WebEx space. We have PBR and the contract white paper in cisco.com. To complete your session evaluation, so this is the last session. So if you like the session, please provide feedback. If you want to hear ESG or PBR more, please leave a message to us. If you need more zoning rule forwarding, we have troubleshooting session by TAC tomorrow morning after this party. So if you really want to learn something technical, please go to see this PBR troubleshooting session tomorrow. With that, thank you for coming even before this party. I really appreciate your presence. Please post any question to me. If you have any question, just come talk to me. Thank you so much. Thank you for coming.